Welcome, everyone. We're coming back to Season 4 of the Prodcast from Google. Can you believe Season 4? It seems like a long time. I don't know. Maybe it's just me. So today we have a great new guest, Pete Pellerzi, who works with actual physical things like buildings and machines and stuff, and not just like bits. So like, Pete, you deal with atoms, I guess. Is that true? I mean, that's wild. You might be the first one on our guest list to do that.
Well, I would say electrons.
Electrons. Okay, cool. And our co-host today is Matt. Welcome back, Matt.
Thanks. It's wonderful to be here again.
Awesome. So yeah, we did a little, kind of a quick fake intro to Pete. But Pete, why don't you introduce yourself properly? Who are you exactly?
Sure. So by training, I'm an electrical engineer. Actually, I was a physicist before that, but I have an electrical engineering degree, and that's where I've spent most of my time doing physical things like large substations, transformers. We build those, install them, and we do the physical part of the Google world. So at Google, I'm a distinguished engineer, which is a title that is relevant here at Google, and I am assigned to the construction team. So we have different groups that make the physical infrastructure. Tons of really talented people, and I work with the construction side, with the physical side of it. And our team is responsible to take the design that's done by our design groups and platforms and so on, make sure that what we do works for the correct generation of server technology, and we bring that into the physical world. We're the ones who physically pour the concrete, even though that's a small part of our job, but we do the foundations, we do the building, we do the electrical and the cooling infrastructure. We do all those big campuses that you see in the newsletters.
Yep.
So we turn it into the physical world.
Give us a sense of the scale of these operations that people...
They can't be that big, right? It's got to be
they can't be that big.
Size of my house, maybe. No?
Maybe a gymnasium.
Typical data
small
center.
Shed.
A small shed, yeah. No, not quite. It's interesting because there's a lot of startup when you do the first one. So typically what we'll do is we'll locate a community that meets our criteria, and we work very closely with the communities to land our not just data center, but our presence there for a long time. So we're not just going to run in and run out. We work with the communities. We work with partnerships with the mayor and the environmental folks. We're very community oriented. And we start building a campus. We'll buy 200, 300, up to 1,000 acres in a community, and we'll responsibly develop it. So you'll see our entrance go in, where you pull in with your car and you badge in at the guard station. Then you see the first building go up, and we always plan for 2 or 3 buildings because you want to make sure you don't do something weird on the first one, like stick it in the middle of the parcel and then you have no place to put the second building. So we'll start planning the site, and we'll build our first building. A typical data center is roughly 2 football fields on end. So if you took a football field and another football field and you put them together, that's the size of the actual server hall for one of our data centers. Then you see all the stuff around them. The electrical infrastructure that supplies the power, then the cooling infrastructure that removes the heat out of the building, generator support when the power goes out once in a while, and then all the other structures, places to eat, offices, entranceway parking, and all that stuff.
So with regards to places to eat, I think that means that you have employees there as well, right?
Well, you do. Of course.
I'm guessing it's not like a fully autonomous system.
No,
once it's been built, I'm saying of course it's like it's a zoo when you're building it out, and it's never probably really done. But like when it's operating, when you have services running, you've got like a slice of Gmail and a bit of AI or whatever is running in that data center. How many are there a ton of ants running around like pushing buttons on machines? Or is it totally autonomous, or somewhere in the middle? Or like, what are we talking about here?
It's somewhere in the middle.
Okay.
Obviously, there's always a push to make things as automated as possible. You don't want to be going up and down rows of machines looking for the one that doesn't have the blinky light. You want to know which one has a bad hard drive. You want to know which one has a bad memory. You want to know which one has a failed power supply, and so on. So those are processes, break fix, are highly automated. Otherwise, you just can't keep ahead of them. But we do have quite a contingent on site. Remember, we always focus in on the machines, which is our primary focus. But there are a lot of other services. For example, 24-hour security, people, gardening, landscaping, food services, cleaning, repairs, general maintenance, and so on. So there's quite a contingent of folks that maintain a so-called, automated data center. They're getting there, but they're not science fiction. It's still humans fixing things.
Fixing things. That's got me thinking about things that go wrong, incidents, concerns, safety. Tell us a bit about how things get managed when they go wrong. What's an incident look like in a data center?
Well, having been in the data center industry for a long time, and you don't give away your age anymore when you get beyond a certain age. So I'll say 25 plus years. That's
Fair.
Sort of
Yeah.
a safe way to say it. But in my 25 plus years, I've worked here, of course, and before here I was at IBM, another large data center provider. Every data center eventually will have some sort of failure. It's just a physical property of the world. Nothing lasts forever. Things break. Things go wrong with no one doing anything wrong. It's just things break. Circuit breaker trips open because the trip unit failed, and so on. All kinds of things happen. That's not really what differentiates success in a company or differentiates a company as being successful. Things will break everywhere. It's how you deal with the break. That's the key. That's the differentiator, at least what I've seen here at Google. For example, Saturday afternoon, 2 o'clock, perfectly fine weather, beautiful sunny day, something goes wrong. Utility fails. Who knows? A million things can
you
go
think of an example of a particular failure that you can share with us? I know that you have exciting stories.
Wait, well, I'm not sure about exciting, but for example, a couple of weeks ago, well documented, the entire country of Chile lost power.
Oh, yeah. That was in the news. Yeah.
Again, we have no control over that. Absolutely zero control. Right? We have no way to do anything about that.
Who could see this coming?
They failed. They had a whole bunch of things. You could read about it in the news, why they failed and so on, but that doesn't matter. We did not experience an outage. So you say, well, why not? This is catastrophic. Well, okay, hold on. When something goes wrong on this proverbial Saturday at 2 o'clock or 1 a.m. in the morning, we have very specific protocols at all of our data centers. So, for example, we open up a video chat immediately, a common video chat between anybody who wants to get on, but usually it's between the facility managers, SRE, and so on. But what happens is folks automatically start to dial in. We get the emergency announce on our email. We'll dial in. What help do you need? So we never strand someone at a data center and say, well, you're on your own, see what you can do. Not at all. And this is the differentiator. We behave like a community.
Yeah. That's great.
And you never leave somebody, just hanging. They know they have the support globally, right? You'll have SRE London, you'll have SRE. Everybody will chime in, and respectfully, because you don't want a million people talking, but you listen. What can I do for these folks? Can I help? Have I had the same situation? What did I do? Are they forgetting something? This way, you're not alone. And this is super successful strategy. Super successful. So when we had this situation in Chile, we have multiple data centers down there, and they lost power through the whole country. So what's the strategy when you have a countrywide outage, right? Like you don't have that written down anywhere, but you have enough people with enough authority to say, yeah, why don't you get a hold of refueling? Let's start refueling right away because we don't know how long this is gonna last.
They're able to adapt. It's
we adapt on the fly,
the team. Yeah.
right? And you've got different people with different pieces, and say, no, you really should look at this and make sure you get that, and you really feel like you have, they have your back.
So it's like cooperative adaptation. That's pretty cool.
Exactly. And this is the secret, right? It's not, nothing, let's make sure nothing ever breaks. That's not a strategy, right? Things break. So, but how do you deal with it?
I think some of our listeners would be really keen to hear how, for their much smaller organization, perhaps with less of an existing roadmap for this distribution of skill, for these many layers of planning over a longer time, how they could find a roadmap for themselves to build this kind of competency forward,
Sure.
what would you suggest to them starting from where they are right now, how to develop their culture for this forward from small, and what kind of steps to take, like an incremental approach to gain this kind of resilience?
It's interesting because I started at Google when we were very small. I mean, when I started, we had just a handful of data centers. And I actually was assigned to finish some of them as one of my first assignments here because we really had just a few. So how do you start from a small organization and scale it, right? Or maybe you're not going to scale it. Maybe this is all you need. You just need a few data centers and you're fine. You need to find trusted partners. So, for example, when we were smaller, we had very low staff. We depended on certain outside architects and engineering consultants, certain trusted vendors, electrical contractors, and so on that had specialty skills. And we used them and we paid them. We didn't ask for charity. They were on retainer and we paid them for their time. But they had the expertise we didn't have. So we said, listen, we're going to set up maybe an on-call agreement with you so that we don't have to write you a PO every time. But hey, when I need you on a Saturday, can I get a hold of, Andy and Tom and ask them to dial in or to go to the site and help the site recover? So we used outside vendors as we built our in-house expertise. You don't have to know everything. You don't have to be capable of everything, but you need a plan. For just something simple like fueling, right? When you go on generator, you need fuel. Well, you need to have the discussion with your local fuel vendors way ahead of time before you need them and say, what can you do? Well, I can get there in 4 hours. Okay, I got it. You sure? Yep, I'll be there in 4 hours when you need me. Okay, now that becomes part of your business continuity plan. So start small and start with the obvious things. Talk to your vendors, put down even just a few words on a business continuity plan. What happens when power goes out? Just 5 bullets. And that really gets it going.
With regards to like the Chile incident, I wasn't involved in that at all because it was just recently. But like I remember some other kind of power incident I heard about somewhere in the world, and they talked about getting refueling, but they had figured out how long it takes to get the fuel, but also how many trucks needed to be in flight at any given time to keep that up, to keep that like they could keep it going basically not forever, but like for a long time. Yeah. But they didn't really, they didn't know there was going to be a really big outage, but they thought like, well, we know how to get like 1 truck of fuel, but like, let's just make a spreadsheet just in case in the future. And they ended up using it. Like that spreadsheet totally saved the day because they knew spin up the 7 trucks or whatever it was that can allow, they can get all the way to the fuel repo and back again before the tank runs out and blah, blah, blah. So that kind of preparation, I think that translates really well, not just to the data center world, but to kind of any kind of, dealing with response. Like you don't have to predict the exact outage, but like just knowing your capabilities and what you can do. And like, well, this is what we have in our shed of possibilities. So at least you know what's in your shed, which is really important, or your tool belt, maybe.
Steve, this does sound a little like doing your postmortems after an incident, looking back on lessons learned, looking at your analysis. How did it match up with what actually went on? And I expect you do quite a bit of that after an incident like that. And to tell us a little bit about looking backward after your forecasting, things you learned, things you got right and wrong. I suspect you do quite a bit of that.
Absolutely. And I'll give you let's stick on that fueling topic for a bit because it's something that you don't do very often. I mean, let's be serious about this. The utility grids are actually fairly reliable. When you need it, it's maybe once in your career or twice it's a very rare item that you need to refuel because of an outage. A lot of times you're refueling because you've used your diesel generators for maintenance purposes. So then you kind of refuel at your leisure. I would challenge you to do as much real world testing as possible. And here's something that we learned that is not obvious. You say, well, how much fuel do I burn? Oh, we burn a truck full of fuel, for X number of hours. A truck is 7,200 gallons, 7,250, I believe, a full tanker truck. So you're like, okay, great. We need one of those every blah, blah, blah. And you do these quick calculations and you think you're all dialed in, you're golden. But you haven't done it physically in the real world. So we did. We had that opportunity. We had run the fuel down on one of the sites a little bit. And we said, hey, let's do this as though it was a real emergency, right? So we started refueling. What did we learn? We learned that the most you can get out of a truck is 300 gallons per minute. That's it. That's all they can pump. So now we had not figured in the offloading time. And the offloading time turned out to be significant.
It wasn't instantaneous?
It was not instantaneous. You have to drain 7,200 gallons out of that truck at 300 gallons per minute, max.
That's a few minutes at least.
And it includes, and that doesn't include setup time with the hoses, connection, disconnection, cleanup, chocking the tires on the truck, getting the drive. None of that was included. And we were very surprised at how long it took. And getting the truck in and out of the gate through security, and so on. We had not thought it through.
That's a great example because, I think often the math, you can do enough math and just totally convince yourself, and then it hits reality, and you're like, oh wait, there was a whole field of equations I forgot about or I didn't know about.
Do it, and that's a lot of the real world testing that we do as part of maybe not an emergency, but as part of a maintenance iteration. Say, hey, what happens if that doesn't start? Or what happens if this doesn't run? Take advantage of every single one of those opportunities because you will learn something new every time.
Let me ask you a question, kind of shifting gears a little bit. When we talk about fuel and infrastructure and concrete and things, I think of that as like looking down the stack, right? Down towards the earth and the fuel or whatever. And then if you look up, I imagine, sort of symbolically, like after a certain point, you get out of the data center and you get into like the kind of the distributed system that's built on top of it. And so this is where these big systems of software are running across many data centers. And then now you're interacting with other teams. You're not really dealing with vendors dealing with trucks. You're dealing with SREs in London, you mentioned, or software developers in Tokyo and things like that. So what are the interactions between your staff, the people that you work with on site, and those folks? Like, is it just, is there a brick wall and you never talk to each other? Are there tickets? Like you mentioned this video conference, the panic room, which is, tongue in cheek. Hopefully it's not actual panic. But are there other methods that you guys is everything figured out, or is there also adaptation going on in that direction as well?
Absolutely. And we talk all the time.
That's awesome.
Before this call, I was on another call with probably 20 SRE folks talking about the next round of dirt testing, ISON testing, and so on that we will be doing this year. It is a constant communication. And the best communication we can have is that our work is totally transparent to the rest of the fleet. So like the Chile situation, the whole country had no power, but we were not impacted.
Can you tell us what DIRT and ISON testing are?
Oh, of course. DIRT is simulated failures. So, and I forgot what the acronym is. SRE, you all should know better than I do. But it's essentially running
disaster recovery test or resilience test.
There you go. It's simulated. What happens if this goes really bad? How do we recover? How do we recover the customers, the data, and so on? So we coordinate with that all the time. And then ISON testing is where we actually fail things off. We actually shut things off and say, what happens if this shuts off? But basically, it's a real shut off. And this is where, we kind of walk the talk. We say, well, you should do this, you should do that. And it's very easy to say that. But we actually do shut things off. And we say, well, what if the utility failed? Well, okay, we could do a simulation, or we could turn it off.
And then how does this affect the upstream systems? Like, are they actually capable of surviving such a thing?
Well, it shouldn't,
yeah.
Right? It shouldn't. But again, like offloading the fuel truck, it's something we don't do very often because we never want to run on diesel, right? For all kinds of reasons, environmental and so on. So we try never to run on diesel generators. But so even more important to actually test it because it's something you don't do very often, which means, it'll be fine. Really, it won't be fine.
Yeah. Out in the world, sometimes they refer to this as chaos testing. That's mostly in the software software failure modes, but like you can imagine similar kind of thing is like induce a little bit of planned chaos into the system and see what happens. Like throw the monkeys in the room and see what they do, kind of thing.
Right. Like we tried to refuel because we had done some maintenance, and we said, well, let's actually try it under emergency conditions, and boy, did we learn a lot. So that's part of this. Again, if your strategy is to never hope that nothing ever fails, that you're going to be very disappointed.
Indeed.
Pete, tell us a little bit where we're going next generation tech, either through power technologies or something new going on in data centers that you can actually share with us or people listening that we wouldn't expect. What's really coming up? What's coming down the road for us?
Density. Density. Yeah, so let me take you a little bit through that. 10, 15 years ago, most of the data center, well, all of the data centers were some sort of Intel AMD chip, and it was very similar to what's in your PC at home. Of course, I'm being very simplistic here, but they were air-cooled chips, meaning they had a heatsink stuck on them and a little muffin fan, and it blew the air across the heatsink and took the heat off the chip, and all was good. And they were fairly low power consumption, 100 watts, something like that, right? Maybe 150 watts. Then the industry, of course, was hungry for more capacity. So you stick more things on the die, you make that chip a little bigger, you stick more chips in there, you build a bunch of chips into one chip, application-specific integrated circuit, an ASIC, which is a conglomeration of things that work together on one sort of package. And that march has been going on forever.
Yeah, Moore's law is part of this, right? Like it's just getting bigger and bigger and tighter and tighter, and
more, right? I want to increase the clock speed. I want the thing to go faster because they're expensive. I want higher return on how much processing power it can do for the thousands of dollars that I've invested. And you've seen the Intels of this world, and now in NVIDIA, I can do better. It's 4 times faster. It's 10 times faster, and so on. So all that is wonderful, and it's not my area of expertise. There's people who have all kinds of PhDs in that can talk much better. My world is power and cooling. So we observe these chips, and they require more power every year. More power, more density, but they give a lot of performance, right? So the business gets a lot of return on their investment. Power turns into heat. Simple as that. I supply more power into the chip or the data center or whatever. It does work. That work turns into heat.
Yeah, at this company, we obey the laws of thermodynamics. Is that right?
Power goes in, does work turns into heat. Mm-hmm. That's the way it goes. So the power that we're providing now is probably several X more than, and I don't remember the numbers, but it's several X more than it was 10 years ago. And it pushes you to certain conclusions. And the whole industry is coming to the same conclusion that we did 6, 7, 8 years ago. So we were ahead of the curve. We said, look, if we kind of extrapolate this up, there will become a point where you cannot put a heat sink strapped to a chip and blow air across it. You're going to reach a thermal limit. You simply cannot get the heat out of that integrated circuit using the traditional aluminum heat sink and a fan. You're going to have to use a higher heat capacity media.
I think I know where we're going. Yeah.
Liquid. Now we say water cooled, but it's not water. They're different fluids, but basically it's water with anti-corrosive inhibitors and things like that. But essentially, the manufacturers, in particular NVIDIA, said we can't get there without a cold plate strapped right to our chip. So we're going to take a copper or some other proprietary material, we're going to stick it on the chip, and you're going to pump cold water in one side and out the other and remove that heat using water, which has 3,000 times the heat capacity as air does per volume.
Yeah, computers notoriously love interacting with water, I think, right?
Well, yes. So we feel, or at least I feel, that Google was extremely forward-looking 6, 7, 8 years ago, where Google said, look, we need to learn how to do water-cooled processors. It was not simple. It was not trivial. A lot of folks are trying to do that now, at the 11th hour. And yes, you bring water directly to the chip. That is a leap of faith.
Yeah, I remember hearing about this a long time ago, and they're like, the first plan was we bring these pipes through the ceiling and bring water down, and then we realized that's a bad plan because drips happen. Like little things like that, man. That's tough.
Well, but we've spent the last, and I can't remember if it's 7 or 8 years. Let's call it 7. We've spent the last 7 years, a lot of really good, sharp people, spending a lot of sweat, perfecting this, right? You just don't run a couple of pipes and, hey, yeah, here, I've got liquid cooled chips. There's a lot to it. Monitoring flows, temperatures, leaks. What do you do if there's a leak? How do you not have this? So we've learned a lot, and that is our secret sauce. And I love when people say, well, what's the secret sauce? Well, let me think. It's 7 years of really hard work by a lot of really dedicated people. And then magically a secret sauce appears.
That's right.
It's hard work, period.
Speaking of expertise and new tech, somebody told me that artificial intelligence is optimizing our data centers for power. Is that a thing?
Yeah. Well, again, it's funny. I guess it used to be called machine learning. And again, I'm not the subject matter expert on this, but it is very useful to us. And we've been using it for several years. I think there was a public announcement on our use of, I think it was called machine learning, ML, but now it's AI, on how to run our cooling plants. And we got some very large savings. Again, I hate to say numbers because then someone always says, "Oh no, but I think it was between 15 and 40%, if I recall."
That's awesome. There's a PUE rating, I think, that
exactly.
Overall.
And here's the secret, right? As human beings, if you sit in front of a control panel and have to adjust the knobs every 2 minutes, you will lose your mind, right?
Not great.
You can't do it.
Yeah.
Also, you don't have predictive capabilities. So we had, again, some super sharp folks here. They took worked with the London folks, DeepMinds, and we came up with this little. It's always little when you don't have to do the work. It was actually a lot of work.
From a distance, from London to here, yeah.
Yeah. They came up with this ML approach to say, look, we can not only take all the inputs from all these devices and find an optimum running point for each one, but we can also take predictive weather data. So I can make adjustments now based on what the weather will be 2 hours from now.
That's amazing.
Right. So it's real-time weather data with real-time operating data. And you watch it, it's fascinating to watch because it will start to turn down the mechanical cooling, a chiller, which is our refrigerant-based air conditioning. It will start to reduce that. And you're like, what is it doing? And then you watch it for a little bit longer. And it makes a decision that if I increase the fan speed and the pump speed a little bit, I can get the same cooling for less power. So it starts to turn down the refrigeration because it anticipates the weather 2 hours from now. Fascinating to watch.
So at Google, we're happy about dealing with large numbers, like we like it. And I like to always say that like a small change in a large number is still a large number. This happens a lot inside of Google, whether it's a good change or a bad change. So in your world, like what is the number that you use to like, tell people about your job and like how it's interesting, and like what is something that you can share about the scale of your world? Like what's going? Is it the square footage of cement, or is it the density of something? Like what's your favorite number?
Joules or watts?
Yeah.
Yes.
Yeah. Choose your units wisely.
Choose my units wisely. There's all kinds of capacities and whatever, but this is what impacts me. I'm electrical engineer by trade, so I'm a electron guy, right? So I'm always fascinated by the other side of the house, which is the cooling side. right? Because to me, it's a little mystifying, right? You make cold water, it goes in, it gets hot, comes back out. You make it cold again, right? Fascinating, right? Because you're always fascinated by what you don't know that well, right? So I went out to one of our sites and I looked at the pipe. And I said, what's that? And they said, oh, that's the chilled water supply to the data center. I said, oh, chilled water, okay. And what's that? Well, that's the return. The hot water comes back.
Yeah.
Oh, okay. So how big is that? It's 42 inches in diameter.
That's pretty big.
Right. So that's the scale. And, you can essentially 42-inch diameter pipe. You can, if you crawl, if you creep down a little bit, you can walk through it. And I was like, that's what it takes to cool one of these things? And they were like, well, yeah. They're very nonchalant, right? Like, oh, yeah.
I'm pretty sure there was a scene about this in one of the Star Trek movies where someone gets transported into one of these pipes and they flow
exactly.
through.
I mean, this particular site, which is one of our larger ones, has a 42-inch chilled water supply in return. And to me, that just, it's like, really?
And I bet it's quickly flowing through that diameter as well. It's not just
exactly right.
lazily going. Yeah,
several feet per minute. And that
awesome.
just sort of, for me, put it in scale. I was like, well, who else has this? And that's just the hyperscalers, right?
Yeah. Would you say, in your opinion, I don't think you have a full understanding of everything on Earth, but like, would you say that the Google data centers are different from other data centers
I would, because they have different purpose, right? And it's not good or bad. Data centers are kind of a personal thing to companies. If you're this kind of company, you optimize for an enterprise type data center. If you're this kind of company, so Google is personalized to what we do. They look the same, right? I mean, all data centers have the same purpose.
Big
right?
box.
Big box. You put electrons in one side, it gets hot. You take the heat out the other side, and you get rid of the heat. But it's all the stuff inside. How do you talk to the servers? How do you interface with the networking? All that is really very unique to whatever company you're in. So it's not a good or a bad, but I think we have a really good mix that's good across enterprise and hyperscaler type, ML. So we have a really good mix. And it's not by accident. It's that we've had really good forward-looking leadership. Like, 7 years ago, our folks in platforms and delivery embraced the water cooling, and that was a really good idea.
Yeah, that's great. Yeah, it's really easy to say no to stuff like that, but like the fact
it
that they
is
say
because
yes is great.
You're like, well, why do we need this? But you need to look 4 or 5 years ahead of time if you can, and say, no, we should learn how to do that.
We have when I talk to companies, so part of my job is talking to enterprises about how they use cloud and data centers, and they're coming from their data centers or some other data center or whatever,
Sure.
and they're moving on to cloud and blah, blah, blah. So one thing that comes up a lot is they like to cite MTTR and MTBF, and I'm curious if how you feel about these statistics in your world, because I know that in my world, in the distributed systems game, we like to say that those numbers actually aren't meaningful to us because it's not a large homogeneous set of components that all have similar failure domains or failure modes. That we actually have novel failures. So like treating this as like it's not a normal distribution. So why are you taking the mean kind of thing? But I'm curious, like if you have a data center full of 11 million similar parts, maybe those numbers do make sense to you at a certain layer, but not at another layer. Like, is there a point where the normal distribution disappears in your world? And like, do you take advantage of that when you're trying to measure your success? Is that a thing?
It is. So we have what you're describing falls under our operations team to monitor and to measure. Certainly, again, I have to emphasize, no one is left alone. We do not throw things over the transom and say, "Well, good luck." No,
your problem
that is
now.
Not that is not the community we have here.
Great.
Just we don't have that. So, what's of concern? The metric that we look at is, availability, right? 99.99, whatever, 5 nines of availability. That's our target. And the way you get to that target is minimize failures, so you don't have to fix things, and then fix things as fast as you can, the MTTR, so your downtime is minimized, right? And that's how you get to that overall availability. How do we get there? We have some unique features or unique opportunities. The manufacturers don't have many customers that have a bigger installed base of their equipment than us. So we actually have better data than the manufacturers of the equipment themselves because they don't have a concentrated pool of equipment that we have. So we see all their latent defects, we see all their strange applications and so on. So we work very closely with the manufacturers. The other thing we do is we built fault-tolerant designs. Again, if you're going to expect something never to fail, that's not so good. We have a very, very robust spare parts program so that if something fails, A, we can recover very quickly using a fault-tolerant design, and then B, we have the spare part in hand. So we can see what fails across a large fleet, even though the manufacturer may tell you, we've never had a failure on that. And they're not lying. They've never seen it because they sell 2 to this person, 5 to that person. But we buy 600. And we say, well, if you have 600 of anything and you have a 0.001 failure rate, we're going to lose one every, 2 years.
Yep.
So spare parts strategy, repair strategy, fault-tolerant design, and working closely with your vendors. And we do really, really well with availability. I would say we're probably the best in the industry.
Yeah, we like to joke that at Google scale, 1,000,000 to 1 odds happens all the time.
Exactly. And it's important not to assume ill intent in your vendors because you say, well, it just broke. You should have told me. They don't know because they don't have a large enough statistical base. So work with your vendors. Again, this is a community sort of argument. Work as a community, not as a bunch of individuals.
Totally. Thanks, Pete. This has been great. It's been cool to, touch grass with the actual data center, touch cement, maybe. I don't know,
Right.
touch steel.
No.
Hold the
Cement is what you mix with the gravel and water to make concrete.
Concrete. I always get that wrong. Well, I appreciate it. We learned a lot, especially that last bit just there. Any final words for our friends about how people can keep up with this kind of stuff? I know we have a cool podcast that Stephanie Wong did a few years ago about how the data centers work in communities, like you were alluding to. Any other resources you want to point people at who are listening to the show?
There's a lot of good content out there. It's a fascinating industry right now. It's really, really exciting. The scale is really exciting.
Still growing, man.
There's a lot here.
It's crazy.
There's a lot here.
All right. Thanks, Pete. Have a great day, everyone.
Yes. Thank you
Take
so
care.
much.
So long.